Okay, so in this video, we're looking at experiment designs. So like I mentioned in the previous video, you're going to watch a video and you're going to answer questions at the same time. And so I will not go through that with you. I'm just scrolling in. So we're going to move past that part of it. Getting there slowly but surely. Okay. So, a sample survey aims to gather information about a population. We're gonna put that in caps. Aims to gather information about a population without disturbing the population in the process. A sample survey are one of a kind observational study. So that would be like when they were studying mice or when they are studying mice. They're in their natural environments and they're not being disturbed. Other observational studies watch the behavior of animals in the wild or the interactions between teacher and students in the classroom. This section of is about statistical design for experiments, which is a very different way to produce data. In contrast to observational studies, experiments don't just observe individuals or ask them questions, they actively impose some treatment to measure the response. The purpose of an experiment is to determine whether the treatment causes a change in the response. When our goal is to understand cause and effect, randomized experiments are the only source of fully convincing data. An experimenter must identify at least one independent variable to manipulate. So this is the treatment, and at least one dependent variable, which is the response. The experimenter deliberately manipulates the treatments and must assign subjects to treatments at random. Experimental units, so your subjects, are the collection of individuals to which treatments are applied. So if we look at example 1, should women take hormones such as estrogen after menopause when natural production of these hormones end? Several major medical organizations thought yes, because women who took hormones seemed to reduce the risk of a heart attack 35 to 50%. The evidence in favor of hormone replacement came from a number of observational studies that compared women who were taking hormones with other who were not. But the women who chose to take hormones were richer and better educated and saw doctors more often than women who didn't take hormones. It isn't surprising that they had fewer heart attacks. In this scenario, wealth, education level, and number of doctor visits are confounding. So we don't know if it was the hormone or any of these variables that caused a reduce in heart attacks. To get convincing data on the link between hormone replacement and heart attacks, we should do an experiment. Experiments don't let women decide what to do. They assign women to either hormone replacement pills or to placebo pills that look and taste the same as hormone pills. The assignment is done by a coin toss, so that all kinds of women are equally likely to get treatment. By 2002, several experiments with women of different ages agreed that hormone replacement does not reduce the risk of heart attacks. In fact, some studies concluded that hormone replacement with estrogen carried increased risk of stroke. So an example 2 is in 2007, deaths of a large number of pet dogs and cats were ultimately traced to contamination of some brands of pet food. The manufacturer now claims that the food is safe, but before it was released, or before it can be released, it must be tested. In an experiment to test whether the food is now safe for dogs to eat, what would be the treatments and what would be the response variables? So treatments would be ordinary size proportions of 2 dog food. The new one from the company and one other type that is known to be safe. Okay, and the response would be a vet assessment of the health of the test subjects. Okay, so note that the test subjects, dogs, must be randomly assigned to either treatment okay. So experimental design, we have 4 principles of experimental design. So we have comparison, which is use a design that compares 2 treatments, such as the one above. We have random assignments, which use the chance to assign experimental units to different treatments. We have control. So keep other variables besides the one you're testing that might affect the response of the subject the same for all groups. And last, we have replication. Use enough experimental units in each group so that any difference in the effects of the treatment can be distinguished from chance differences between groups. Okay, so we have example 3. So we're planning an experiment to see if the new dog is safe to eat, or dog food is safe to eat. We have established that we will feed some dogs the new food and some dogs food that is known to be safe. So the principle of comparison. In this experiment, how could you implement the principles of control, random assignment, and replication? So for control, we could control the portion sizes. Control the environment. My goodness, I'm like typing with my toes this morning. So pen, amount of water drank, amount of exercise, and sleep. Restrict experiment to single breed of dog. Finally, we have the random assignment. So that is to assign dogs to the 2 different treatments randomly by flipping a coin. And we have the replication. So assign more than 1 dog to each treatment to allow for variability among dogs. A lot for you to write. Pause if you need to. Okay, so we have strategies to improve experiments. So use a controlled group. Researchers vary the independent variable for the experimental group, but not for the control group. Any differences in the dependent variable for the two groups can be attributed to the changes in the independent variable. So for example, medical, that should be, see there, researcher wants to test a new drug believed to help smokers quit. 50 people volunteer for the study. The researcher randomly divides the smokers into two groups. One group is given nicotine patches with the new drug, while the second uses ordinary nicotine patches. The researcher then measures how many in each group quit smoking. You've also got blinding, so keeping anyone who could affect the outcome of the response from knowing which treatment, oh, that's supposed to be in caps. Treatment have been assigned to which subject. A double-blind experiment is when both the subject and the experimenter don't know which treatment the subject has been given. So for example, in the earlier pet food example, the vet should not be told which dogs ate which food. So use a placebo. So often simply applying any treatment can induce improvement. So a fake treatment that looks just like the treatments being tested is called a placebo. So placebos are the best way to blind subjects from knowing whether they are receiving the treatment or not. And then we've got blocking. So groups similar experimental units together, then random assignment of subjects to treatments is carried out separately within each block. So in the previous dog food example, different breeds of dogs may respond differently to the food. Blocking by breeds can remove that variation. So we've got example 4. So a firm wishes to test the durability of 4 tire types that we'll call A, B, C, and D for convenience. Here are 4 possible studies that might perform. In all cases, the cars are to be driven on a track under controlled conditions until its tires are deemed worn out. The response variable for each experimental unit, so a car, is the number of miles the car drove with the tires. Each of the first 3 designs contains at least one serious weakness. Comment briefly on them. The 4th design is called a block design. So state what the blocks are and explain what the advantage is of this design over design number 3. Okay, so we've got 4 Cadillacs of the same type are purchased new from 4 dealers. One gets tire A, gets outfitted with 4 type A tires. One gets B, one gets C, and one gets D. So this design involves no replication. Without replication, you can't tell whether any difference in wear is due to the type of car type or the car differences. The next one, we have 12 Cadillacs of the same type are purchased new from 4 dealers. 3 get tire A, 3 get tire B, 3 get tire C, and 3 get tire D. So you can't infer to all cars what you observe only on Cadillacs. So this was true in design 1 as well. Okay, so there's no variation, they're all Cadillacs. So that would be the issue for this one. For 3, we've got 12 vehicles in different types. 12 vehicles of different types are randomly selected from a list of many vehicle types, and then are randomly allocated into 4 groups of 3. One group gets tire A, one group gets tire B, one group gets tire C, and one group gets tire D. So the difference in wear on the tires may be due to the types of car in the group, not the type of tire. So 4 Cadillacs, 4 Fords, and 4 Volkswagens are purchased. One of each gets type A, one gets type B, one gets type C, and one gets type D. So the blocks in this design are the car types. If there is a difference in tire type, it would be most easily detected with this design. Okay, so our 4th scenario is the best. We've got quite a few replications. So we've got 4 Cadillacs, 4 Fords, and 4 Volkswagens. We also have a variety. We have different types of cars. So unlike our other example where they're all Cadillacs, we've got different types of cars. And so keep that in mind while you're doing any of your work or creating your population and surveys. Okay. I hope it goes well today. You know where to find me if you have any questions. Don't forget that your ISU check number 1 is due. You do have the documents that explain everything. It was on the first day that I posted it. So that'll help you along to know what to do and what is expected. Good luck.